Hello everyone. We continue to study the Z-domain analysis module of discrete systems. Let's analyze the Z-domain analysis method of discrete systems today. First, let's analyze the definition of Z-transform and the Z-transform for typical sequences. The first content is the definition of Z-transformation. Z-transformation is divided into unilateral Z-transformation and bilateral Z-transformation. Its definition is as follows. Then everyone can see the biggest difference between these two transformations is that the value range of k is different. When k goes from 0 to positive infinity, we call it unilateral Z-transform. When k sums from negative infinity to positive infinity, we call it the bilateral Z-transform. Then, in practice, we need to grasp the Z-transformation form of common signals. It will be helpful to our later study. Let's analyze the Z-transformation of common signals. The first signal is unit sample function. The expression is as follows. When k equals to 0, delta of k equals to 1. When k is not equal to 0, delta of k takes 0. The graph is as follows. We can solve according to the definition of the transformation. After the definition of the Z-transform is calculated by the corresponding summation, only one item can be summed. So, the Z-transform corresponding to delta of k is 1. We express the convergence in the full plane as follows. Second function is unit step sequence. Expression is such a form. When k is greater than or equal to 0, all sample sequences take 1. When k is less than 0, take 0. As shown in the figure for such a sequence, we solve according to the definition of the transformation in the form of such a series. So, if you want to convert this series through deduction, we can see that when the modulus of z is greater than 1, it is convergent and converges to z divide z minus 1. Then the expression of its z transformation is z divide z minus 1. Pay attention that the convergence domain is that the modulus of z is greater than 1. This is the result. The third function is the z transformation of the hypotenuse sequence. Then find the z transform for k epsilon of k. It is more troublesome to directly solve according to the definition. So we use an indirect method to solve. We know from the previous example that the expression of z transform corresponding to epsilon of k is such a form. Let's transform this formula. Differentiate z to the power of -1 on both sides. The derivative result is as follows. Based on this result, we can analyze. Multiply both sides by the -1 power of z to get such a result. Then look at this result. At this position, it corresponds exactly to k epsilon of k. Look at such a function. The corresponding result of solving the z transform. Then the final result is the square of z divided z minus 1. And so on. We can also get expressions of the transformation of other functions. For example, those formulas, the form as shown in the formula. Then this function inside and this symbolic form shows the result of derivation one by one. Then, after derivation, multiply by minus z. Then make the corresponding derivative is such a nested expression. Note here that k is a discrete variable, and the form of the z transformation obtained is a form of continuous variables. The fourth function is exponential sequence. Exponential sequence is the most widely used. We first look at the sequence on the right, that is, the expression of the z transformation of the Carroll signal. Let's solve it. We still use the defined form to solve. Then we can find that with the modulus of z is greater than the absolute value of a, convergence to z divide z minus a. So the result of its z transformation is the result of the above. This a has several forms. We see that it can be a real exponential signal. It can also be an imaginary exponential signal. We have two forms. Then, after plugging that into it, the result of its corresponding z transform is as follows. This is the result. It has a great universal significance. Therefore, the z transform of the Carroll sequence exponential form is needed. This needs to be graphed firmly. The characteristic of its convergence domain is that the modulus of z is greater than that of A. That is, an area larger than the circle. Similarly, for anti-Carroll sequences, we find its z transform. After corresponding proof solution, we still use the defined way. Finally, converges to z divide z minus a. But the difference is that the characteristic of its convergence domain is that the modulus of z is smaller than that of a. The area within the circle is exactly opposite of the sequence on the right. This is the result of the z transform corresponding to the right sequence and the left sequence. Then everyone noticed that the results of their z transformations are the same, but the difference is that the corresponding convergence domain, in other words, the same z transform. When the convergence domain is different, the original sequence corresponding to it is a different arranged sequence. Therefore, it is necessary to indicate the convergence field when seeking the Z transformation. Fifth common function, sine and cosine sequence. First, we look at the unilateral cosine sequence. According to the form of Euler's formula, it can be decomposed into the form of the sum of two exponents. So we can use the Z transform just now to solve. The result is as follows. After finding the Z transformation of these two imaginary exponential signals, let's organize and merge. We get the result of the Z transform of the cosine sequence. Similarly, we can get the result of the Z transformation of the unilateral sine sequences. These two common forms need everyone to understand. The above is our analysis and introduction to the common signal Z transformation. I hope it will be helpful. Thanks. That's all for today.